Okay, ready to go. Just a practical thing. The group isn't all that big, so let's make it interactive. If you have a question, don't wait till the end where you might have forgotten the question. So just raise your hand or whatever, draw attention, and then you all can ask your question. In the next 50 minutes, I'll be talking about synthetic test data generated by machine learning. Now, just to see a bit what the level of knowledge is in this group about synthetic data in any form, be it manual or with tools. Just a raise of hands, who of you already has some experience with synthetic test data? There's quite a lot of people, which probably explains why you're here. Now, to make this a bit tangible of what we're going to talk about, let's do a little quiz. So what you see here on the screen, and to avoid the left-right confusion, I numbered them 1 and 2, is 2 screens. So on each screen is a payment with the usual information, the amount, and then where it goes from where it goes. And they can either be synthetic or fake. Fake just sounds better, so I'll be using fake. Or they can be real. So the question will be whether the number 1 and then for the number 2, whether they are real payments, what you see, or are they actually fake synthetic generated. So whoever of you thinks that the number 1 is fake generated by an algorithm, please raise your hand. Just a few people, a bit more, not that many people. So, and whoever thinks that the number 2 is a fake one, as quite a lot more people. Is anybody thinks that they're both fake? We should all raise our hands. They're actually both fake. Now, if you look at the yellow part, I will talk about this project that we did, but when we created these synthetic payments and we send them into the test environment, we got complaints from the end users because they say, what the hell are you doing? Why are you sending these thousands of payments into the environment? So then what we did was in the identification, the yellow part, this is the payment identification in the system. We added the word test. So just to help us to make the distinction between the ones that were real and synthetic. So it's actually very difficult to see what is real or what is synthetic. So that gives you a bit an idea of type of stuff we're going to talk about. Now, for me, this story started about 3 years ago. One of my projects got cancelled, and I found myself with a data scientist, without a project. So I come from a testing background in banking, also other industries. So in my team, we were doing quite a lot of testing. So what we figured out was that we asked the question, what can we possibly do in testing for which we need a spare data scientist? And the first on the list was test case generation. So we said we should look at using perhaps machine learning to generate test cases, but that turned out to be a very difficult one. We looked a bit at what was available, and that was a tough one. So we didn't do that one. Now, if anybody here in the room has a solution, I'm really interested, so please let me know. The second one on the list was generating synthetic test data. So that one, we looked into it. And then we Googled a bit. We found some research papers from MIT at the time. And that's where we started. So my name is Wim Blommaert. I'm leading a team at ING. And this is what we do full time. So we have already done 12 projects. And what we're trying to do now is to scale this in the organization. And that's what I'm going to talk about a bit. And I'll have a few examples of projects, what we have done. Now, the lessons learned here is that if ever you find yourself with a spare data scientist, keep him. Do something with it. Now, why would we bother? Why invest in the generation of synthetic test data? Well, we all know that when we deploy code to production, stuff happens, and not the stuff that we want. So that's why we do the testing. We also know that to do the testing, we need test data, and the testing is actually only as good as the test data we have. We can have good test cases out listed, but if you don't have the data to allow these tests, then that will not work. Now, getting test data can also be a problem. It can be hard work and costly, because perhaps you need to copy that data from production, or you'll have to write all kinds of masking scripts to mask that data. Or you want to do them manually, you want to make test data manually, so that can be quite some work. It can be slow because perhaps you're not the one doing that copy, so you might have to ask another team that has access to production and they can do the copy, but perhaps they are doing something else, so you'll have to wait. So we have known cases. We did a survey where people would say that on the average they had to wait like 2-3 weeks before they actually would get the data. So by that time, perhaps your test isn't even necessary anymore. It can be a privacy issue or nightmare, because you're not just allowed to copy some data from production. Either you will not be allowed. I will talk about one payments project in which they were simply not allowed to do that. Or you will be allowed, but they will ask you to do the masking. And that can be complicated because you have to do it in a consistent way. If you have joins between tables, your masking needs to fit between those two tables. And the last point is that if you're going to get data, for instance, from production, that data can be incomplete for 2 reasons. One is you're doing the masking, so you might be destroying some of the columns that you actually needed for your test. And another thing is that the cases that you actually want to test might not even exist in production. For instance, at the start of Corona, the Belgian government issued special collateral that was for small businesses, so they could use that to still keep loans from the banks, so the government would give collateral for that. But when we wanted to test that at ING Bank, we couldn't copy that from production because that was a new thing. So if we copy data from production, those collateral don't exist. So that's a number of problems we have when we want to get test data. With synthetic data, we try to solve these problems. And I will show you with the examples with 2 projects, is that if you do it in a proper way, it can be much faster. You can really push on the button, get your data. You can fully automate it, which makes it low cost also. The coverage can be good. I will show that we can generate special cases, so we can instruct the algorithm to spit out certain specific cases that we want. And synthetic data is very good from a privacy point of view. So for instance, in GDPR, they don't say much about synthetic data. They actually just say that it's not in the regulation, so that you don't have to follow the rules for that. On the left, you see that actually whatever we do on the right with the synthetic data, we have a huge leverage because, for instance, in ING Belgium, we have a lot of people involved in software development. That must be around 1,000 people, that order of magnitude. All these people in some way are involved in testing. Developers, unit testing. Some people are actually doing that testing full time. Some people might be involved in getting the test data set up. So that means that whatever we do with the synthetic data, we have actually a lot of potential for people we can help. Now, how did we get here? Where does this come from, this synthetic data generation? It's actually not so much of a surprise because these things have been around for quite a while. So we are now familiar with these deep fakes, and they are actually getting very good. So it's getting very difficult to make the distinction whether they are actually real or fake. I'm quite sure that a lot of people must have thought that this was a real one. So this technology, generative AI that can generate images, that has been around for quite some time already. Now, there is a bit more serious use of that also. For instance, in the medical sector, they will use this. So imagine they have a software that you show with X-ray pictures, and the algorithm has to say whether there might be a tumor in that picture, so then a doctor can then check whether this is actually the case. But they don't always have enough of real pictures, luckily. So what they do is, since years, they have already been making synthetic pictures, and then they mix them with the real pictures to train the algorithm. So on the right, you have the real images, and on the left, the fake ones. But to be honest, if you switch them around, you would notice, because they're pretty good. And it turns out that the boxes, the color boxes, the blue and the green, this is a measure of how good we can train an algorithm. And the blue box is with real data, only real data, and the green is with a mixture of real and synthetic. And actually, it turns out that if you train your software with a mixture, it actually gives a better result. So it's better to mix them up than even if you had enough of real pictures, you might still want to mix in the synthetic ones. Now, since a few years, we can do this. So this is tabular data. So the stuff you would find in Excel or in relational databases. This type of data is most of the data in a company like ING. This is most of our data. We do have images, but that's really not a lot. So most of the data we have is tabular data. And since a few years, we can do the same technique on tabular data. Now, to just give you an idea of what that actually means, the bottom screen is real. So this is data from a project we did for a system that sends loan information to the ECB, to the European Central Bank. Of course, it's just a snapshot, just a few rows, just a few columns. So the bottom one is the real data, and the top is the fake or synthetic. Now, the idea is that the fake data should be statistically similar to the real one. Now, what does that mean? For instance, if you look at the interest amounts, so that should follow the same distribution. So like minimum, maximum, medium. So it should be similar amounts, let's say. If you look at the amortization type column, you see that in the real data, there's a lot of bullet payments. Bullet payment is a loan that gets paid one shot at the end of the loan. So yeah, we would expect that in the synthetic data, we then also have a lot of these bullet payments. It doesn't have to be the exact same amount, but just the same proportions, let's say. And it even learns that we have the maturity date, so that's the end date of the loan. And we have the inception date, which is the start date of the loan. Yeah, in all logic, the end date of the loan should be after the start date, right? You shouldn't end it before it got started. Now, some of you might now be checking this on the screen. If you're doing that, pay attention to the second row, which is 2, 3, 6, because there it isn't true. It's reversed, actually. I don't know if somebody had already figured that one out. Sometimes the algorithm will not get it right, because I will explain it's a statistical approach. But then we can force it. We can put a constraint to say, whatever you do, this date must always be bigger than that date. But that's what it looks like. So it should be statistically similar, which is at the column level, but also correlation between different columns. Gartner, as far, of course, as advice of Gartner goes, they predict that by the end of this decennium, that data to build models, that most of that data will be synthetic. I think they say 60%. Now, they don't tell here something about testing, but I think with testing, it might be a bit slower, but it will go the same way. So we will gradually more and more use synthetic data and use less real data. And perhaps at some point, we'll just use more synthetic than real data. Or we will mix them, because that might actually work better. Now, how does it work? At ING, we are using a software called Synthetic Data Vault, which is a Python software development kit, so it's Python code. This technology was originally developed at MIT. So In some labs at MIT, this was developed. And then when it became too big, too much users, there was a spin out. So a company was created from that almost 3 years ago. So this company is called DataCibo. So we work with them on this technology. We co-create the product. But that's the technology we use. So it's basically Python algorithm. Now, of course, that still doesn't tell you how it works. So this is how it works. So how does that work? It's actually just the same as with the Trump pictures. You have to build a model which is trained from the real stuff. So real pictures from Trump, or in this case, you need real data, real tabular data. So we start from a training set, top right, which is real data. We feed it through our Python code, and then that code will build a statistical model, which is like what I explained, what that means. And once that model is created, we can then go the other way around. So we can then say, okay, from the model, I want you to sample, create 10,000 rows. And then you get to the synthetic data on the bottom left. What you put in can be small. We can train from a few thousand rows, and then we can create a lot of data. For instance, for this project, we trained from 10,000 rows, and we generated 30 million rows for a performance test. So the input can be small, the output can be big, and that took like 5 hours to do. There are two basic sorry, yeah.
How do you verify the 30 million rows of synthetic data?
Whether they are any good?
Yes.
Sorry. We have a lot of metrics that are available, because this is actually a good question, because how do you know that you're actually not generating a lot of crap? So we have metrics that can help us to do that, which they are statistical in nature. So we have the original set and we have the result set, the synthetic. And there are mathematical methods by which you can assess whether the resulting distributions, let's say, how good they compare to the real. So those metrics exist. They can be applied on numerical values, categorical. There are also metrics like Pearson, Spearman. I don't know if it's all statistical. There are metrics by which you can measure the correlation between columns. There are privacy metrics. So it's very important, because the thing is that when we give it to a project, we don't know unless we apply the metrics. So we always apply those statistical metrics. And then another thing is that we always agree with the project what would be the goal, their goal. So we can also measure, because the statistical metrics by all be okay, but that still does not necessarily mean that they can achieve the goal. So there is always, let's say, the goal level. For instance, for the performance test, they wanted to do a decent performance test. You can quantify what that means, then see did they achieve that. And before you give the data, you can check statistically these metrics. So the good news is, because it's statistics, that these metrics they just exist. I mean, they have been developed over the last years. So yeah, that's a very good question, because otherwise, and we also have privacy metrics, so we can also measure the privacy of the data. That answers already a bit one of the approaches, which is a statistical approach. So one way of doing this is to use statistical algorithm, which makes sense, because after all, you want to build a statistical model of the data. So that's the one we use the most of the time. And one of the things we use is tabular calculation. Some people might know this. This is something that was already used as from 2005, I think. This is not new stuff. Tabular calculation existed before GANs were invented, before the neural networks were actually massively used. And that's the second approach, is to use a neural network for this, which can be a GAN or an encoder, decoder, that type of thing. The thing is that neural networks don't scale very well, so they work on small models, like 1 table, 2, 3 tables, but once it gets bigger, 10 tables, 20 tables, that doesn't work. And then we can use the statistical approach. So yeah, without going into the details of the mathematics, that's basically how it works. Now I will I will look into 2 projects that we have done. Well, actually 3. The screenshot that I explained with the statistics was from this project with loan data to the ECB. That was one project. This is a second project for payments, and that's actually the screenshots that I shown for the quiz. This is from this project. So what we did there, and I'll just quickly describe a bit the flow of things, how that worked. So we took 10,000 real payments from our production system. Now payments, they are messages, they are size queue, so that's easy. It's like a single table, so we can very easily apply either statistics or GAN. Both would work. It's the most easy thing to do. It's a single table. We took about 10,000 of these. We run it through our software, well, or 5,000. We run it through the software. We build the model. Once we have that model, then from that we can generate the synthetic payments. We have a platform to do that because, of course, the data we take from production, as long as we don't make them synthetic, they should not leave that environment because then they wouldn't be privately safe. So we keep them there. Once we have the synthetic data, then, of course, we can copy it to a lower environment. That's okay. So we generate synthetic data. Let's say we did 10,000 synthetic payments, and that took less than 5 minutes. So the whole modeling, sampling, actually, I think it was less than 2 minutes. So for 10,000 payments, 2 minutes, you're done. Of course, you first have to set it up, but then every time you want to sample, it just takes 2 minutes. Then we injected them back into so we start from production, we make synthetic data, and then we inject them in the test environment, so where we want to do the test. So this was actually our acceptance environment where users were also testing, hence the complaints we got and why we had to put the test in the identifier. But then we had a little problem because you then push these synthetic payments through your payment engine, but then it gets to the back office. So the back office is all the systems that will actually handle the payment. For instance, money has to be moved from an account to another account, for instance. And some other things have to be done. But that back office system was data that was actually copied from production and where masking was applied. But that meant that when we pushed the synthetic data through the payment engine to that back office system, which is actually basically real data, the back office system, with masking, that back office system went like, sorry guys, I don't know what that is. Because the account numbers, they were all synthetic, so that back office system doesn't recognize them. So then the only thing that was missing, and that's the green box, we had to match the accounts. So what we did is we took the synthetic account numbers that we generated, and we just replaced them with real account numbers from that back office system in that acceptance environment. And then the back office was okay, then it happily processed the data. Now something else we did, I talked about completeness and special cases. If you do not specify anything particular, then the statistical sampling will sample a bit of everything. So if the black line, which is like a Gaussian curve, let's say, represents the model, and of course some things are more likely to be sampled, the ones in the middle, and some are less likely, the ones in the tails are less likely to be sampled. But it will sample a bit of everything. The yellow circles, they cover the whole model, which means that if you want to have good test coverage, you'll probably want to sample a lot of payments just to make sure that you got a bit of everything. So that's where you sample 10,000 payments, and which is the same as you would copy from production. You probably also want to grab a lot of payments just to make sure that at least the ones you want to test, they are there. Now we can do something else, which we call conditional sampling. We can actually say to the sampling, do not do this statistically. I do not want you to cover the whole model. I just want you to stay in the green box. And for instance, the green box can be, I only want you to sample payments with less than €5, or payments that will be executed today. And then that means that we do not have to sample that many payments. Then with a few payments, we can actually sample exactly the ones we need for the test. So for instance, if our test was, I want payments with small amount, payments with a large amount, and I want payments executed today and tomorrow, which we call memo payments. So that's 4 options, and we just want 5 of each. So then we can instruct the model to exactly generate those 20 payments. And that's just more easier because then you do not have to cycle 10,000 payments to your test and check all 10,000. You just have to check the 20 and that will cover whatever you needed. So that's a very interesting way of getting the special cases. So what does that bring for such a project? So we can generate 10,000 payments for them or 20 in a matter of minutes. Before we did this, they would have to create these manually. And in SEPA, it's a format in HTML. So it's like a 3-page HTML just for one payment. And you have to type the whole thing. So imagine you want to do that 20 times, or let alone doing it 10,000 times. So it saves a lot of work. It's much faster also because if you want 10,000 other payments, you push the button and 2 minutes later they are there. It's of course good from a privacy point of view because whatever is generated is synthetic data, and therefore I'm not going to say it's 100% safe, but it's at least much safer than what you would get from masking. And we have metrics to measure it, which is the good news. And it's much more complete because either you can generate a lot of payments just to make sure you cover a bit of everything, or you can just generate the 20 payments and then exactly the ones you wanted. So it's actually scoring very good in all of the 4 areas. The second project we are doing, and this one we're still on it, well, the one of the payments also, but this one is a bit new still, is the testing of APIs. And this is actually something we really think this might be very interesting for us because we have a lot of microservices APIs in the bank and more. So what is this about? If you want to test an API, one way of doing it is that you hit the real endpoint of the API. So you're testing with a real thing. That means in your environment where you want to test, that API is there and it's up and it's running, and you can hit the endpoint and send something and something comes back. So for instance, if I send 1 + 1 to that API, then it's supposed to answer 2, and I can check whether that is correct, and that's my test. So that's a bit of a connected test, but in some cases, it's actually interesting that you could do a local test where you wouldn't actually depend on having the real API available in the environment. For instance, because that API might not always be up and running, and then, so if you can do it locally, you can continue your testing and not be dependent on that API running. And for that, you can use a mock. We use WireMock for that, and actually I think in another room, but please don't leave, there is a presentation on the use of WireMock. But yeah, there will be the video, so you might want to watch that. We use, it's an open source tool, which mocks APIs. And then this idea is the same. Instead of sending to, you will not hit the endpoint of the real API, you will hit some endpoint of a mock. You will send it 1 + 1, and that mock is supposed to send you back 2. Of course, it allows you to test your application. It does, of course, not allow you to test the API. That would be the reverse. We are looking in that one also. So this is so that you can test your application without actually having access to the real API. Now, how does that work? That mock doesn't know much. So you have to tell the mock what to do. So that's a mapping table. So you have to give that mock the mapping table of what requests you can send it and what then should be the return. So typically these requests are, if there are REST APIs, they could be in JSON format. So we give to the mock, we say, look, if I send you this mock, then you should send this back. So that whole mapping table you have to give it. And then you can just hit these endpoints, and that mock will just happily reply whatever you told it to reply. Now, that's all very nice until you discover that this is what they look like. This is one of these replies. So on the left is the request, and on the right is the reply. So that means you would have to tell the mock this whole thing. In some way, you'll have to type it up, or you have to script it. It has to come from somewhere. So, oops. Don't know where that went. So yeah, if you want to do one of these, that would still be acceptable. But if you want to do 10,000 or even 10, you probably will stop after a few. This is actually one we generated synthetically. So it's a get, so that's like a read in API language. So you see, we at the endpoint, and we give the identification of a customer. And then on the right, we get back the JSON structured response, which is actually saying that this customer has 2 physical addresses and has an email and a phone number, and then a bunch of internal identifiers that's just stuff for the bank. But this is one request reply pair. So we can generate this. That means that if you need 10,000 of them, 2 minutes, you got them. Now, how do we do that? Again, as I explained, we need to train from real examples. So here what we are looking for is that we need the real pairs of requests and response, and those we will pass through our algorithm, and it will build a model of what these look like, and then it can reproduce them. And we need a few thousand of these. So what we did in this case was that these APIs, they have a logging. So when these calls happen, these things get logged in a Kafka topic, and that's where we can get them. So we got these loggings, a few thousand of these pairs. We run that through our software. It learns what they look like. It builds a model. And then we can ask the model to generate 10,000 of these. And this is a read, but you can also do it for like a write, a put, or so to update stuff. So that means that you can then give to the mock these synthetically generated mappings, basically, between input and output. And then that mock will, then when you hit the endpoints with these customer ideas, then that mock will answer with whatever we generated. And again, you could also then generate special cases. I could say, for instance, I want to have a customer with 5 physical addresses, or I want to have a customer with 4 phone numbers, or I want to have a person with no addresses. I don't know if that's even possible. But that means that, again, instead of generating 10,000 randomly synthetic request response pairs, we could also guide the model, and just the same as with the payments, say, okay, I'll only generate 50 of them, but they will be a bit specific depending on the cases that I wanted to test. The advantage of doing this is exactly the same as in the other for the payments. And today we are doing this with 2 teams. But again, if they would have to do this manually, that would be so much work that, and actually that would mean that they might not use the mock, because once they discover that they can only use the mock when they have these mapping tables and that it's a lot of work, then they might actually not be inclined to use it. So what we can do is to say, look, no problem, we can generate this for you. It just makes it easier for them to start actually using these mocks. So it's much cheaper and faster, and it's all the same things, and we can generate special cases and so on. Now, the next slide will be my last slide, and that's something I want to give you. But we still have some time left. So I would say, so either I just go to that last slide, which is okay, because I think this is the last lecture. But yeah, I don't know, perhaps there are some questions.
I had another question about the training data. The model that you're training, does it run locally? Because it's important that the production data doesn't go outside into the cloud.
Yeah, so in the setup we have, it's what we say on-prem, so we run it locally, and indeed the idea is that we should never let the data get out, I mean the real data. We do let the synthetic data get out. We have 2 projects where we send synthetic data to external parties, but real data shouldn't go out. And some of the solutions that are available in the market, they depend on public cloud. So that for me was always difficult to understand, because why would I send my real data to somebody's public cloud to get back synthetic data? That's kind of defeating the purpose. So yeah, no, it's on-prem. It never leaves our environment. Any other questions before we? Somebody has a question? Oh, sorry. Yeah, the lights are in my eyes. I'm very sorry.
I have a question.
Yeah.
Basically, if you look at the picture of Trump, what you get is that you get random pixels that get some kind of orange color that statistically are very close to the face of Trump, but their eyes are forgiving. They say, okay, that's Trump over there. Now, if you get test data that is also a little bit of randomized data, how do you then validate that your results are okay if you pass the random input data through your application? For example, if you do real tests and I say, okay, I transfer 100 euros to your account, you can validate afterwards that that money has been transferred. But if the data is generating is like randomized, it can be 98 euros, it can be 102 euros. So how do you then validate that the result is correct?
Now, it's of course not really fully randomized. It follows a certain distribution. So if certain, like for age, for instance, if most people are of a certain age, then in the real data, then in the synthetic, that will be the same. And we will not generate people with negative age, hopefully, and probably not somebody with 300 years, because the model will never have seen those. If in the data we give it, there's an error and there's a 300-year-old person, then it might actually generate that. So in that sense, that's not really random. And then, yeah, as already explained, we have metrics to check that. For instance, you have things like, yeah, fancy names like Kolmogorov-Smirnov, which is just a mathematical calculation, which can calculate whether, let's say, I have age in the real and in the synthetic. It can actually take these data and say, how close was the synthetic from the real? It can actually just calculate that. And it can do it for numeric and for categoricals. There are also metrics to measure correlation. So you would measure correlation between 2 columns, for instance, the maturity date and the start date, let's say. You can then run those metrics on the real data and see, okay, those are highly correlated. And then they should then you can compare, because then they should also be highly correlated on the synthetic data.
Only about the input data, but you want to test your application, so you send that input data to your application, and then something comes out of it, and that's basically what you want.
But the application doesn't know. It just, for the application, data is data, and the concern is, of course, whether the synthetic data is a good representation of the real data, but the application doesn't.
Then how do you validate that your application is working?
Just the same as what you would have done if you would run real data through it. That doesn't change. So for the tester who's actually validating, for instance, the tester wants to test if I send a payment of 1 billion, what happens? That doesn't change if the synthetic is 1 billion or the real. From a perspective of the application doesn't know, and the tester will just do the same tests.
The tester then knows I transferred the 100 euros from this account to that account, he sends that message in, and he checks what comes out, and he sees, okay.
Yeah, that's just the same. That's the test that the tester anyway would have done with real data.
If you have partly randomized data, still statistically correct, how do you then still validate that your application is doing the right thing.
Well, the sensible thing to do is to generate specifically the cases you need. Like to say, I want a small amount, a big. For instance, an amount of 1 billion, even if it's generated, might actually not be something you want to test. And that's why I think you go to the scenario where you only generate 20 payments, but you have your little test case list. You say, I want memo, non-memo, small, and you just see that the 20 cover whatever are your cases, and then you check them. And yeah, if you do the 10,000, then it's true, you will end up with 9,000 payments you are checking, but they were actually not very relevant, or they were just duplicates. But the same would be if you copy 10,000 payments from production, what people very often do. It would be, at least this solution gives you the ability to generate a small set of test data which matches what you wanted to test. I hope that explains a bit. Yeah, we still have time for questions. If there are questions, of course.
What's the problem with generating tests?
Test cases. Well, how we check that is because that was 3 years ago, so we didn't have a lot of. Even for this, we had no knowledge. It was all Googling and finding out. What we actually just do is we looked at, is anything already happening in the bank for that? We looked at, do people talk about it in conferences? Then we checked, are there research papers on it? So we actually looked for references if anybody was doing that stuff. And then we see that there wasn't not a lot available. And then some of the research papers were actually just pointing to the fact that this was a problem. For me, the big problem is likely that how do you measure? Because these machine learning algorithms, they are based on some kinds of a goal-driven loss function. How does the algorithm know that it's doing the right thing in the case of test cases? Because that means you have to train that machine learning based on some goal. Like, when does it know that it has generated a good test case? And that was something we had no real good answer for that. And if you don't have such a loss function, which can drive the whole training, then it will not work. But that was 3 years ago, so once we get bored with this one, I'm pretty sure we'll get back to the other one. Because, yeah, that would be a massive thing, of course, if you can generate test cases. So, yeah, I'm not sure, actually. We didn't find a lot of references, and we thought that, by definition, not having a loss function was a problem, and then we just left it there. And then we moved on to this. So, we can still take questions, I think. Yeah.
You mentioned that this is for tabular data. You also mentioned SEPA payments, which are basically XML documents. So can you just train it with the entire SEPA payments and it will generate syntactically correct SEPA payments?
No, what we do is we just consider them to be a table, which in the case of SEPA, that would be like a single table, a flat structure. With the APIs, it could be nested, so that would be like a parent-child structure schema. So we first pretend it's tables, we do our stuff. So it's actually a pre-processing where we read the JSON or the HTML, we put it in a data model with parent-child structures, we do our stuff, and then at the end we just script it back to the format. So it's just a packaging thing. The tool does not necessarily today do that. That could be something that could be added later, but it's basically scripting that we do. But the essential is that that is actually just a matter of packaging. The content is synthetic, and then it's just a matter of putting it in the right format. But that doesn't change the content anymore. So that's something we could easily do. And that's actually very nice, because the problem of making these test data is actually the fact that it's an HTML. Because if it was a single line, you could probably easily type it up or script. But it just gets complicated because it's a few pages of HTML with, how these things go in HTML, so that makes it really hard. So yeah, it's scripting we do. But it's one script can handle all of them. Once you know these formats are published by SEPA, so you just write a script and you're done. Any more questions, or we have 6 minutes left? or we can go to the last slide. We're done with the questions. Okay. You can actually try this on your own if you want, because there is an open source version, which is either that URL or you can scan the QR code. This open source has 1 million downloads, so it's not something, it has been tried by many people. There's a lot of documentation, there's also good support, there's a Slack community, there's a lot of people around that can help you with that. So actually, if you want to try it out, you can, it's open source, it's free, you can just do that. There's a lot of documentation also, good documentation. Of course, it's Python code, so it's not the most difficult Python code, I think. You could probably just easily, and anyway, you're all good developers, so that shouldn't be a big problem, I guess. So yeah, my thing is that if you want to try this, you could actually do it. The only disclaimer is that the open source has some limitations, but the only limitation I think you need to be aware of is that if you want to do a very big model, like 20 tables, that's not going to work with the open source. So you can do single table, or 3-4 tables will still work. But yeah, that means that you can still try that out. Yeah, that was actually my last slide. Thank you.